Huan, and I'm a postdoc at Carnegie Mellon University. I'm very honored to receive the Rising Star Award, and I would like to thank the organizers of this great workshop. In today's talk, I'm going to introduce my works on formally verifying the robustness of neural networks, including our alpha-beta quorum verifier, which is the winner of this year's VNN competition. Neural networks are very powerful function approximators, and it has been demonstrated to be very successful in many real-world scenarios, such as image classification and image captioning. The input of a neural network can usually be images, text, or videos, or any generic data, and the output of a neural network function, fx, gives us the desired results, such as a classification label or a sentence. Despite its successful in many fields, the lack of robustness in neural networks has been a well-studied topic. So people found that when adding a small and imperceptible noise, called adversarial examples, the adversarial perturbations, to a benign input image, the neural network can surprisingly predict something that is completely irrelevant to the input. The images that look visually similar to the benign inputs but triggers bad behavior of a neural network is typically called adversarial examples. Since the discovery of adversarial examples, people try to get rid of them and proposed many tricks to defend against them. However, it is common that stronger adversarial attacks can break many existing defenses, and it's really hard to show that a new defense won't be broken on the newer types of adversarial attacks. The main topic of this talk, neural network verification, is about formally prove that a neural network has a certain property, such as a property on robustness, which would be saying that no adversarial example exists around a benign input image. Just conducting adversarial attacks is not sufficient to solve this problem, because it cannot always guarantee to find an adversarial example, even if it exists. Although neural networks are successful for many tasks, we know it's hard to guarantee certain properties and behaviors, such as no adversarial examples exist, because the neural network is usually highly nonlinear and non-convex. And we don't really know what's the real function the function approximator is approximating. It can be a simple function, or it can be a complicated function where we don't really understand its behavior under a certain region of inputs. Sometimes it's really hard to show to prove even simple properties. For example, in this scenario, we want to prove that output of fx is always positive, given the input of x between 0 and 1. And if we want to prove this just by sampling, that's not going to be practical, because you cannot sample an infinite number of points. You can always miss some certain regions of the function, especially in the high dimensional region, where you would require exponential number of samples to do a sort of like grid search on this neural network function. And the gradient-based method also has some troubles, because the neural network function is non-convex, so you can easily get stuck at some point where gradient is 0, and you cannot always find the minimum value to show that the function is always positive. So this problem of verifying the property of a neural network, such as those simple ones, actually NP-complete for general neural networks. And the goal of neural network verification is to develop tools that can help us see into the black box function and prove some useful properties, such as safety, robustness, and fairness. So in this talk, I will mostly focus on robustness properties, but the same principle can also be applied to other settings. So consider a very simple binary classification classifier, where the input, we have input x0, and the output after the neural network is fx0. We call fx0 is positive example if it's greater than 0, and it's a negative example if it's less than 0. In the robustness verification problem, where we want to show that when the input is a set around x0 rather than a single data point x, we want to also show some property of the output. So in this case, because the input is a set, the output is a region. It's a range between FL star and FU star rather than a single number. And to prove the property of the network, we have to consider a set of infinite points input in the input perturbation set. To formally say this problem, we can solve this non-convex problem where we want to find the minimum value of the fx inside the perturbation set fc, or we can also solve the maximum of the function as well to get the upper bound. But here we'll just focus on one set of problem. We are trying to minimize the problem. For example, if x is originally a positive example, if we can find another x within the perturbation set C that change the objective value to -1, then we can actually flip the label. So that's actually a adversarial example, so the model is not robust. If the f star is greater than 0, we can show that we can prove that actually the function is verifiably robust because even the minimum value is greater than 0. So there are a few different methods to solve this problem. The first one is called complete verification, where people try to solve this problem exactly, try to solve to the global minimum of this problem. Of course, this is the NP-complete problem, and usually you need to use mixed integer programming, so that can take hours even on a very small neural network. And the second approach is called incomplete verification, where people just find the lower bound of this minimization problem. So if the lower bound is greater than 0, you know the true objective is also greater than 0, so you can still show that the network is robust under this input. And another way is to do adversarial attack, which I just optimize this function using gradient descent, where we can find the upper bound of f star. So if the upper bound of f star is less than 0, then we can show the network is non-robust. Verification and adversarial attacks are actually two connected approaches to evaluate the robustness of neural networks. Where in adversarial attacks, you want to solve the minimization problem by upper bounding it, and a stronger attack would be close to the true minimum of the problem. And in incomplete verification, you want to lower bound the function, and stronger incomplete verifier will have a larger lower bound. And the strongest attack and the strongest incomplete verifier will meet at the same value, which is ground truth global minimum of the function f star, and which can be obtained by a complete verifier. So a complete verifier is also the strongest attacker and also the strongest verifier. So in this talk, I will basically show how to make neural network verification scalable and also powerful, starting with incomplete verification, where I developed an algorithm called Huan for feed-forward neural networks, and that was later extended to general neural networks. And also, I found ways to further tighten the bounds with GPU optimization. And lastly, I will talk how to convert this very efficient bound propagation-based method to a complete verifier, which has strongest possible power. All the techniques combined leads to the alpha-beta quorum verifier, which is the winner of the verification of neural network computation this year. So we start with the incomplete verification problem. We want to find a lower bound of this verification optimization problem. So quorum is a bound propagation-based approach to give you a lower bound of this optimization problem, where instead of doing sampling or just doing gradient descent, we actually can give you probable lower bounds and upper bound of the fx function. Although we don't know what exactly the black box function look like, we can actually give you two provable bounds, a lower bound and upper bound for the function, so that you can study the behavior of this function. The algorithm works roughly like this. So consider if there are no nonlinear functions in the neural network, for example, there are no ReLU functions, then all the weights of the network can be actually multiplied together because there are no nonlinear activation functions, and actually the network becomes a simple linear classifier. And in this case, you can easily get lower and upper bounds of the network by using something like Cauchy-Schwarz inequality, which is pretty easy under the LP norm perturbation setting. The challenge part is in neural network you have non-linear functions, and the idea here is to use two linear bounds, a linear lower bound and linear upper bound, to bound the non-linear activation functions. So for example, for ReLU function here, if we know the input of the ReLU is between L and U, which we call pre-activation bounds, we can actually use a linear lower bound and linear upper bound to bound the ReLU function, such as everything is still linear and we can propagate the linear bounds as I show here. In the quorum verification algorithm, actually we propagate the linear lower bound for the output neuron, with respect to a hidden or input neuron. We propagate from last layer to the input, and the goal is trying to get lower bound for the input fx. So roughly speaking, the algorithm works like the following. So we start from the last layer where we have equality fx equals to z3, which is by definition, and we propagate this equality to the previous layer, which is a linear layer, just by plugging fx equals to w3 z hat 2, because it's linear, so this is still a equality. And now we need to deal with the ReLU activation function, and we want to still propagate some lower bounds. So how to propagate the bounds through the ReLU function and still maintain that, to make sure this thing, the bound is a sound bound. So that is solved by two steps. The first step is to try to derive a linear lower and upper bounds for nonlinear functions such as the ReLU function. As I demonstrated earlier, so we can actually use a linear lower bound and linear upper bound to bound the ReLU function. The interesting here is that for ReLU function, the tightest upper bound is unique, but for lower bound, actually you have flexibility where you can actually choose the slope of the lower bound, and you have an optimizable parameter alpha here, which we'll utilize later. So, and after that, I just propagate the bounds based on the sign of the matrix before this diagonal matrix, which represents the relaxation. For example, if we want to compute the lower bound, we just take the lower bound of the ReLU. If the number of the weight matrix is greater than 0, basically you just consider a worst case scenario and select the lower and upper bound accordingly. After that, you propagate bounds through the ReLU layer, and you encounter another linear layer, which is easy because we can just plug in the definition z2 equals to w2 z hat 1 into the inequality. And you have another ReLU function where you just do the same kind of linear and upper bounds for the ReLU function, and you find a D matrix based on the sign of everything before the matrix, and also you use the linear relaxation of the ReLU function to get a linear lower bound of the neural net function with respect to Z1. And finally, we will reach the input layer, and what we will eventually have is a linear lower bound, where it's a linear lower bound of the output and the input x. And this lower bound, as you can see here, can be done in a very efficient bound propagation manner. We are propagating inequality from the last layer to the first layer, sort of in a similar manner as back propagation. So, and it can be efficiently implemented on GPUs. Essentially, what we have is like we have a lower bound, which is guaranteed to be a lower bound for any fx within a perturbation set C. And we can easily solve the worst case value by solving another easier linear optimization problem. For example, we can lower bound the function as a green point here, because it's really hard to find the true global minimum. But here we can, by linearize this function, we can find a relaxed lower bound quite easily. So, but the issue with this bound is that first, it's hard to understand. Because it's not friendly for people outside of field, and it's also hard to derive for all different kind of architectures and hard to implement. Originally, the paper was just on feed-forward neural networks, but later we generalized the idea on a general computational graph where we can derive bounds in a back propagation manner. We call it backward bound propagation. We can propagate the linear inequalities through a general computational graph, which can be a arbitrarily complicated neural network such as LSTM or transformers. And we can also handle both input perturbation and weight perturbation because they are just the inputs of the computation graph, and we don't really distinguish between them. So this process of propagating the bounds is quite complicated. But the good news here is we can hide all the complicated details from users. We developed a library called AutoLearPa, where you just define a computational graph in PyTorch, and we can give you bounds of the function. You don't need to consider any details. You just need to supply our library with a definition of your computational graph, which is just in a similar way of you define your computation in PyTorch, and it can be arbitrarily complicated. And we do have a demo here which shows how to use this library, where we show on an 18-layer resonant model where we define the model and you can just compute the bounds using our library, and you don't know too much details of all the bound propagation process I introduced before. And after that, let's go back to the verification problem. Huan is an incomplete verification algorithm, and it's usually too weak to give tight bounds on a model, especially for models trained by adversarial training, not by a specialized certified defense method. For complete verifier, actually we aim to solve the problem exactly given unlimited time, because it's still a NP-complete problem, so you still need an exponential time to solve the problem, but just to see like how you can solve the problem as fast as possible. So there are a few approaches to solve the complete verification problem. So of course you can directly do gradient descent, but that doesn't work because you cannot guarantee to convert to global minimum, and you can only find the upper bound of the verification problem, which is actually a adversarial attack. And the existing approach formulates the problem as a mixed and integer linear programming problem, where you can use Scalable or some other solvers to solve the global minimum, but it's really, really slow. And typically, people also relax the problem, relax the integer constraints as a non-integer, that's a conditional constraints. So this is a relaxed problem using linear programming, which can only give you a lower bound of the objective. So this is the incomplete verifier. It's gonna be much faster than the MIP-based formulation. And the bound propagation-based approach I introduced above can actually be seen as a special case of linear programming solver, where we can actually show the two actually are equivalent under a specific formulation. But if you use this bound propagation-based method, the benefit is that you can compute the bounds much faster with GPU acceleration. So to achieve completeness, typically people use branch and bound. So branch and bound, you can apply branch and bound with linear programming-based incomplete verifier to achieve the global minimum. And in this work, we study how to combine branch and bound with our very efficient bound propagation-based methods on GPUs to also solve the global minimum of this problem. So our approach is to combine this very fast bound propagation-based incomplete verifier that can be accelerated on GPUs with branch and bound to achieve complete verification, which were only possible with very slow LP or MIP solvers, and we actually can be 3 or 4 orders of magnitude faster than those slow CPU-based algorithms. So how did we do that? So let me first introduce branch and bound for really quick. So the verification problem is still trying to prove the function is greater than 0, giving a x input giving a perturbation set. But we know that the ReLU neurons actually have 3 different cases between depends on the pre-activation bounds. If we know the input of the ReLU neuron is always greater than 0, in this case, the ReLU neuron actually becomes a linear neuron where there's no nonlinearity and no relaxation needed. And for the case where we know the upper bound of the input of the ReLU is always less than 0, we can actually delete this neuron directly because it's always outputting 0. The only tricky case is which we call unstable ReLU neurons, where the input of the ReLU can both be negative and positive. But in this case, using the branch and bound framework, we can actually split the unstable ReLU neurons into 2 cases, where we have a linear case or we have a always be 0 case. The 2 cases can be handled by adding speed constraint to the verification problem. The speed constraint is very easy. It basically says a neuron is greater than 0 or a neuron is less than 0. After we adding the speed constraint, we can use some incomplete solver, for example, Huan, to solve the incomplete verification problem. If we can show that objective is greater than 0 for a sub-problem after adding a speed constraint, we can actually verify this sub-problem. For the case where the sub-problem still cannot be verified, where the objective is less than 0, we can further split the next unstable ReLU domain and build a search tree here. So our approach involves combining bound propagation with fast and GPU acceleratable incomplete verifier. The pros is, of course, they are much faster than LP-based verifier, and we can do this thing on GPU. And the cons are the bounds are usually much looser than typical linear programming-based verifier, and in this bound propagation process, we cannot handle these speed constraints like z greater than 0 or z less than 0 directly. And this can lead to infeasible splits and splits and incompleteness, which is not desirable. So to solve the two challenges, first we proposed alpha Huan, which is an extension of Huan, where we optimize the lower bounds of the ReLU relaxation. As I just mentioned, for the ReLU activation function, it's flexible to choose what lower bound to use. And we can actually use gradient ascent to optimize the lower bound by choosing different alpha values here. And we can actually give a tighter bounds because we are solving a maximization problem here, and we are maximizing the lower bound means we are getting a larger lower bound, and larger lower bound means it's actually tighter. And another trick we used here is that, as I showed before, to split the ReLU neuron into three different cases of active neuron and inactive and unstable neurons, we need to know the intermediate layer bounds L and U. And in this formulation, we can also optimize the intermediate layer bounds as well in a single optimization objective. We can see that we can both choose the optimal lower bounds, like the blue lower bounds here, and also we can tighten the relaxation of the ReLU neuron. So actually, the area of relaxation, which is the purple here, is much smaller than the original problem. So by doing that, we can actually get a lower bound that is better than the linear programming-based verifier. And the second approach we use here is called beta Huan, which extends the bound propagation approach to handle the split constraints. And we can also formulate the split constraint as the optimization problem where we optimize another set of parameters called beta to tighten the bounds. At high level, if we encounter a split constraint during the bound propagation process, we can add the split constraint as a Lagrangian or KT multipliers, and we can optimize this additional variable beta. So eventually, the bounds we get are like this. So we have the additional parameter beta, which we can also optimize to increase the value of the lower bound to make it tighter. And after you solve the inner minimization problem in closed form, you'll see that the optimization problem on beta is actually a concave problem, which we can actually converge to the global maximum. And also we can recall that we also have alpha Huan, where we have the alpha optimization parameters, and we can optimize alpha parameters and beta parameters together to get the best possible bounds. Actually, those helps us significantly by optimizing the bounds. We do the evaluation of our verifier on a complete verification benchmarks where we have a lot of baselines here, and here we show that how many examples we can solve with increasing running time. We can show as our method, which is a light green curve here, solves a lot of properties much faster than all these existing baselines, thanks to the tighter bounds caused by the optimization, and also thanks to the faster GPU acceleration. We can actually do 2 to 3 magnitudes faster than classic linear programming-based verifier. And our verifier can also be used as a incomplete verifier where we can set a very short timeout threshold, like 3 minutes. In that setting, we can also verify much more images than the existing approach. For example, previously, semi-definite programming-based relaxation achieved the strongest performance on adversarial trained networks. But here we can significantly increase the percentage of images we can verify, and that's actually not too far away from the upper bound of the verified accuracy, which is by conducting the PGD attack. Actually, we are closing the gap between the verified accuracy and PD attack accuracy on the MNIST dataset. And on the CFAR, there's still some gap where we do much better than the existing approach, and we are much faster. Finally, by combining all those techniques together, we have the alpha beta Huan verifier, which is VNN-COMP verifier of the verification of neural network computation. In this year's competition, there are 12 teams participating, and each team submitted a verification tool, and each tool is evaluated on a standardized AWS environment by the organizer to be fair. And there are 8 benchmarks. Benchmarks have image classification and also control and database application scenarios. And each benchmark has tens to thousands instances which we want to verify. And each tool wants to verify as many instances as possible within the timeout threshold. There are 12 tools from different universities like Stanford, Imperial College London, and our tool is called Alpha Beta Quorum. And there are also some other tools which can also utilize GPU to do the verification. And there are 8 benchmarks, 8 scoring benchmarks, and also unscored benchmarks from different applications and control, image classification, and also database. And there are small networks and also large networks. And finally, the results look like this. So our verifier, Alpha Beta Quorum, actually solves the most number of instances on all benchmarks. On some benchmarks, we solve actually significantly more images on like CFR10 ResNet and ERN benchmark. And on some other easier benchmarks, we solve the same number of instances as our verifier. And overall, we were able to win this competition. And you can find more results of this competition in this link. Overall, although we achieved success in this year's competition, I still see the neural network verification problem as a very challenging problem. A lot of progress has been made during the past few years. Like in 2017, we need to solve the same set of problem using a few hours, and 2018 we can do it in a few minutes. But here our verifier can solve them in 10 seconds. But it's still hard to prove properties for really large networks such as those used for ImageNet, where I expect we still need 100 times more scalability here. But we do see a huge progress during the last few years, where we can get like 1,000 times improvement since 2017. And I hope with more advanced techniques we can eventually verify some large networks to give some provable robustness guarantees. So that's the end of my talk, and you can find the code of my verifier in this link. And I'm glad to take any questions from the audience. Thank you.
Thank you, Juan, for giving the nice talk, and congratulations again for winning the award. And also the award and also the competition. Yeah.
Thank you.
Yes. Any question from the audience? Feel free to unmute yourself and ask a question.
Okay, so I have a question. So Juan, great talk.
Thank you.
You mentioned we expect to have a larger gap for the adversarial trained model if we use the incomplete verification, right?
Right.
I'm wondering what's the state of the art of this gap?
Yeah, so the gap actually, so there are many factors here. So first it depends on like how large the model is. So the larger the model is, the larger the gap is. And also depends on the method you used for doing the incomplete verification. If you use a simple approach, like for example, you're using some approach from 2018, or just using Quorum without of extension of branch and bound, you can verify very little of images on the MNIST dataset, for example, in this setting. But if you're using stronger verifiers, you can making the gap between the upper bound by PGD and the lower bound of verifier accuracy smaller and smaller. And on MNIST, I think we're closing the gap, so there is still like maybe 8% or whatever in this gap for this specific model we evaluated. But I know there are larger models which can be much more difficult. But for CFR, the gap is actually still quite large. You have like 20% of gap. But so far, our approach is the best one so far. But I believe there's still a better approach to be developed to further closing this gap.
Okay, thanks. And you mentioned larger model requires more careful studies. When you say larger, which means higher number for the weights or the higher number for the layers?
Actually, the difficulty is related to the number of unstable ReLU neurons. So, because in branch and bound, as I mentioned, if a ReLU neuron is unstable, then you have to split the neuron into two cases. And the problem is actually itself exponential. has the exponential complexity. And the complexity depends on the number of unstable ReLU neurons. And of course, if your network has more neurons, it can have more unstable ReLU neurons. So that's why a larger network is, of course, harder to verify.
I see. So is there any connection between model pruning and the model verification? Because it seems that pruning is a natural way to identify the vulnerabilities of the neurons, right?
Right, indeed. So I think if you prune the models in the way that you're also trying to reduce unstable ReLU neurons, which determines the complexity of the verification problem, actually I believe you can get better verify accuracy. I'm not sure if that has been explored or not, but I do believe there's a connection here, because if a ReLU neuron is unstable, and if this neuron is not that important, you can prune it, right? You don't have to keep this neuron, and you don't need to split this neuron, so you reduce the verification time.
Mm-hmm. Okay, yeah. Sense. Yep.
Yeah, okay, I think we are on top of the hour and we are delayed by 8 minutes. I think that's fine. And thank you, Huan, for a great talk.
Thank you.